Well, that was as if on cue. Thank you. Good afternoon, and thank you for attending this installation of the Stocker Lecture Series. I want to say a little bit about the Stockers. Paul Stocker was a 1926 graduate of electrical engineering. He founded Lorraine Products, a very familiar company here in Ohio, after working at Bell Laboratories. In 1978, he bequeathed $8 million to the Russ College of Engineering and Technology. I think the total gift to the university was about $16 million at that time. If you think about inflation over that period of time, it's a pretty significant gift by any means, a very large gift. His wife, Beth, continued that record of giving and friendship until her death in 2004. So their total combined giving was over $31 million in dollars not adjusted for inflation. So those folks have been generous benefactors to the Russ College and actually to the university. They funded a number of things outside the Russ College. So I'd like to introduce our speaker, Dr. Henry Petroski. So before I do that, I'm going to tell a little anecdote that I told him earlier when we had coffee, and that has to do with a lunch that I had with a community member yesterday, and I was talking about Dr. Petroski coming and giving a lecture, and he said, well, what is he going to talk about? And I said, well, he's going to talk about the difference in cultures, I think, between engineering and science. And he laughed immediately, and he said, culture? Engineering? I said, former friend? So, Dr. Petroski received his bachelor's degree in 1963 from Manhattan College and his PhD from the University of Illinois, the one in Urbana-Champaign, in 1968. He's a registered professional engineer in Texas, and he's a chartered engineer in the country of Ireland. He and I had an interesting discussion about pride in profession and that being tied to professional registration. So he and I are at least of like mind about that. He's published more than 75 refereed journal articles in fracture mechanics and related fields, 17 books and hundreds of articles in newspapers, magazines, and trade journals. Among his many publications, and I mention this one specifically because, and I had to confess to him that I had at least started reading this book, and it's been a while, so I don't remember if I had completed it. And he seemed to be okay with that. But it's called The Essential Engineer. I think the subtitle is the thing that struck me, and is the reason that I picked it up, is Why Science Alone Will Not Solve Our Global Problems. And I bet he's going to address, at least parenthetically, some of that today in his talk. He writes the engineering column for American Scientist, and he writes a regular column in Prism Magazine, which is the premier, well, it's the sort of generic magazine publication for the American Society for Engineering Education. Among his many honors, including honorary degrees from 5 different institutions, he's a distinguished member of the American Society of Civil Engineers, a fellow of the American Society of Mechanical Engineers, and of the Institution of Engineers of Ireland. And he's an elected member of the American Academy of Arts and Sciences, the American Philosophical Society, and the National Academy of Engineering. And I'd be willing to bet that's a unique combination of organizations, Dr. Petroski. After teaching at the University of Illinois and the University of Texas, and working as a group leader at Argonne National Laboratories, he joined Duke University in 1980, where he's currently Alexander S. Visick Professor of Civil and Environmental Engineering and Professor of History. So, please welcome Dr. Petroski.
Thank you, Dean Irwin. It's a pleasure to be here. I can't see the audience because the light's so bright, but I hope you can see me and the slides. So what I want to talk about is engineers and scientists, and I want to talk about engineering and science, and I want to draw some distinctions that are not always appreciated. And I want to consider whether it's important to distinguish between scientists and engineers. This is an image that was very popular in the, about the middle of the 20th century. And as late as the late 20th century, you could write to General Electric, which produced this image, and ask them for permission to reproduce it, and they would give it freely. Most people will recognize the gentleman on the left. Not everybody recognizes the gentleman on the right. But these two people really epitomized science and engineering for a long, long time. It's, of course, Einstein and Steinmetz. Steinmetz was an electrical engineer from around the turn of the 20th century into the 1920s, and I'll say more about him later. We all know who Einstein was, I believe, but I'll tell you some things that you might not have known about Einstein. This image is very interesting in many ways. The scientist, Einstein, is very well dressed, most people would say. He looks like he's dressed for winter. The engineer is dressed a little differently. It looks like he's dressed for summer. In other words, they don't even look like they're standing in the same weather. And engineers and scientists very often are at odds and don't quite see eye to eye. And I'd like to elaborate on that. These are two pictures, covers from Life magazine. Life magazine was very widely read from about the 30s into the later part of the 20th century. On the left, what is featured on the cover is Fort Peck Dam. Probably everybody appreciates this is a great engineering achievement. But where are the engineers in the picture? It's what they produce that is the focus of the image, not the engineers themselves. On the right, in 1957, the Soviet Union launched the first artificial satellite. That was called Sputnik. And that was big news because it took the United States quite by surprise. Well, what's happening in the picture here on the cover of this magazine? Well, these are scientists trying to figure out, what Sputnik is doing, what its orbit is, because the Russians didn't exactly, or the Soviets didn't exactly tell us that. So here we have an engineering achievement, and the engineers are virtually invisible. They're dwarfed by the achievement, whereas the scientists are almost bigger than the world in trying to figure out this thing, which, by the way, was another engineering achievement. Science and engineering often appear in the news, but sometimes it's hard for an engineer to recognize what is actually happening in the story. This is something from your own campus's news release, I believe it was. And it was that a trio of scientists is to receive the Russ Prize for this year. The award, as the sub-headline said, is the top bioengineering honor in the world. Now, if there's a difference between scientists and engineers, then why are scientists receiving an engineering prize? I'd like to elaborate on that in this talk. Let me just say a few things about a quote from this press release. Ohio University and the National Academy of Engineering, they announced that the bioengineering profession's highest honor, the Dolores Fritz and Dolores Russ Prize, has been awarded to, and 3 people, and these are the scientists from the headline, for LASIK and PRK eye surgery. The medical profession is really very closely allied with the engineering profession. It deals in accomplishments that are tangible, things that we can actually appreciate. They're not just theoretical, they are things that get down to earth. Well, these people that won this prize, these scientists, were in fact scientists. They were chemists and physicists. There were also some of them identified as inventors, which is closer to engineering, and I'll also say more about that. But I hope by the time I'm finished this afternoon that there'll be an understanding of how this can happen, how scientists can in fact receive an engineering prize. It's much less likely, I might add, that an engineer would receive a science prize. Other examples of this, if you remember about 3 years ago, in Chile, there were a bunch of miners, I think about 30, trapped underground when the escape routes from the mine, the exits, were blocked by rock slides. It became a real worldwide story to try to rescue these miners. So from August to October, for months, they were actually trapped down there. And of course, the big problem was, how do you get them out? It was clear that you weren't going to be able to dig out the rock slides in time to save them, so something had to be done. At first, there was this supply borehole drilled in order to just get them food and other necessities. But then to actually get the men out, the miners out, took a big achievement. And that was done by coming up with this capsule. So they were going to drill this hole that would be a diameter large enough to contain this capsule, and the capsule itself was large enough only to contain the largest miner. And this was then going to be lowered down, it's about 600 meters, and then bring the miners up one at a time. And this was also a very big news story. Well, the Wall Street Journal reported on this. Chile's rescue formula, quote, 75% science, 25% miracle. Appreciating that there was a certain amount of maybe luck involved too. But if you read the story beyond the headline, it said it was 75% engineering and 25% a miracle, according to someone who was actually there. Now, what happens from a story in which engineering is given credit for the design of this rescue capsule? What happens between that and the headline where science is given credit? Well, if they're the same thing, it doesn't matter. But I'll hope I'll convince you by the end of the lecture that they're not exactly the same thing. But what is it that causes engineering to be changed to science? I doubt you find a similar story where scientists are discovering a new particle that the headline gets changed to engineering. So are these words synonymous? Does science equal engineering and vice versa? Does science include engineering? If that were the case, then, well, this is not that important. It's a question of using a more general term for something more specific. But could it be that, in fact, science is considered superior to engineering, and reporters, writers, scientists themselves would rather attribute things to science than to engineering? Another example was the Deepwater Horizon. If you remember, summer of 2010, the oil rig that was in the Gulf of Mexico, named Deepwater Horizon, there was an explosion. The explosion led to a fire. The fire led to the sinking of the rig itself, and that led to the rupture of the well head that was about a mile underwater. Well, the immediate question was, after it's no longer possible to save any lives, about 11 workers on the rig were actually killed, then the question became, well, how do we stop this oil from gushing out a mile below the surface of the Gulf? Well, was this an engineering problem or a science problem? Basically, in oil exploration, the scientists get involved in the exploration. The geologist, might be able to contribute quite a bit about where it's most likely that you'll find supplies of oil. But to actually do the drilling, to design the drilling equipment, to design the pumping equipment that's going to bring the oil out and so forth and so on, that's generally considered an engineering task. Well, what happened? This was in the Gulf of Mexico, as I said. The people involved, which were the oil companies, the operators of the rig, and so forth, they were mainly engineers, and they got together in what they called a war room and tried to strategize how we're going to stop this oil from gushing. And it all had to be done remotely because you had to send robots basically down to operate at a mile beneath the surface of the Gulf. Well, it was quite widely reported in the news that the Secretary of Energy, Stephen Chu, who every time he was identified in the newspaper was identified as a Nobel laureate in physics, clearly a scientist, he was sent down from Washington to take charge. The engineers weren't going to be able to figure this out, so the implication is. Well, Chu disappeared from the story quite soon thereafter because this was a very difficult engineering problem. You can't stop this oil just by writing some equations on a board. It turned out that they eventually did stop the oil, but I think it was about 4 months that it took. There was a lot of ad hoc effort being made. There was a lot of trial and error, and there was a lot of embarrassment. But eventually the well was capped, and this is a sort of a memorial that now sits at the bottom of the Gulf, recalling those 11 people that were killed. Another example where engineering and science are not put on an equal basis, and in fact, engineering is sort of relegated to an inferior position. Many an engineer's view of science versus engineering reporting in the news is that when there's a successful launch, it's considered a scientific achievement. An unsuccessful launch of the space shuttle in this case is called an engineering failure. And this is sort of a joke among a lot of engineers, especially those who matured during the space race in the 1960s and 70s. But in fact, it can be documented. You can go take a paper of record, a newspaper of record such as the New York Times, and you can see that this is actually the nature of the reporting. Within the same story, you can find this kind of, I'll even call it a bias. The reporters and science writers appreciate the difference between engineers and scientists, between engineering and science. Now notice I refer to science writers. I've never heard them referred to as engineering writers. Again, the implication sort of being that engineering is included in science. The New York Times has a special section every Tuesday that's called Science Times. And not infrequently, there are stories in that section of the paper that are really engineering stories. I once gave a talk to a group of science writers, as they were called. It was the Association of Science Writers or something to that effect. And they were holding a meeting in Durham, North Carolina, where I live. So they asked me to talk to them and give my opinions about engineering and science. And I told them that really things like bridges, as an example, I spoke about bridges. These begin with concepts, often with actual physical drawings. They don't begin with equations from a physics book. One of the science writers, a very distinguished one, actually, he challenged me. He said, no, that's just not true. They begin with equations. They begin with math. Well, that's simply not true. And let me give a few examples of that. There was a situation back in the 1990s, as the millennium was approaching, the year 2000, especially in Britain, there was a desire to have a lot of special projects that would be called millennium projects, and they were to produce monumental pieces of engineering, art, architecture, but a lot of them ended up being bridges. And one of them centered around the Tyne River, which flows between Newcastle and Gateshead, up in the northeastern part of England, Newcastle upon Tyne. Newcastle especially was the birthplace of, well, the railroad locomotive that really set the railway revolution in motion. And these cities, both Newcastle and Gateshead, were thriving at one time as industrial centers during the Industrial Revolution. So a lot of bridges developed to make passage from one side of the river to the other easy. And this is a picture upriver of some of the historic bridges. And you can see there's sort of an arch theme to them. This is how they developed. Well, in the meantime, these two cities became, well, less than thriving, and they wanted to recapture some of their old glory. So Gateshead in particular said, well, we're going to sponsor a design competition. Engineers and architects are usually familiar with design competitions. It basically lays out a problem and said, give us your best ideas. And then the best idea is selected and the project is hopefully executed. Well, here the problem was stated as follows. One way of revitalizing this area, these two cities, is to develop their riversides. And one way of accomplishing that and encouraging that would be to have a bridge, a pedestrian bridge in particular, that would take visitors from one side of the river to the other and vice versa. And by the way, let's also make it a bicycle bridge. But now what's happening here? Okay. I have to put my glasses back on. Oh, well, it took care of itself, didn't it, right? Okay. 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 So where was I? So you want a bridge, you want a pedestrian bridge, but it had to, and engineers are used to this. Problems come with constraints. You just don't open it widely and say, we want a pedestrian bridge. Because the people that want that bridge, they have something in mind. They not only want to get the pedestrians and bicyclists back and forth, but they also want to keep the river open to shipping. So it has to be a bridge that takes pedestrians across on a more or less level. And at the same time, the bridge has to then open and allow ship traffic to move up the river. Furthermore, the bridge has to harmonize with the historic bridges that are upriver, as we see here. Well, what do you do if you want to enter this competition? Do you go to a physics textbook and look up in the index bridge? I don't think so. I challenge you to find a physics textbook that will give you a new idea about bridges from an index entry. Basically, what engineers do is they think, they become creative, they imagine, and often they sketch. Sometimes on the back of an envelope, sometimes on a napkin in a restaurant, sometimes on the tablecloth itself. But just the barest minimum of an idea. And that's what's in the upper left here. The top is the idea of a bridge that's closed. The bottom is a bridge that's open. They didn't go to Newton's second law and said, well, a bridge has to satisfy Newton's second law of motion, therefore F equals ma, therefore a bridge falls out. It just doesn't happen that way. That's not to say that the bridge doesn't have to obey Newton's law, but that's a different matter. Well, on the very bottom here, the bottom right, that was the winning entry, and it got built, and it's called the Gateshead Millennium Bridge. This is it in an open position, And here it is in a closed position. And I hope you'll agree that it does appear to harmonize with the bridges in the background. It accomplishes the objective of getting pedestrians and cyclists across the river on a more or less level. They don't have to climb up and come down. And it is quite an addition to the riverscape, if you will. It's quite a revolutionary bridge. This is not something that was copied from some other city. This was a true engineering / architect contribution. And I say / architect because there were teams that were actually doing this, architects and engineers. So this is an example of how a bridge really comes to be. Bridges do not begin with science. They begin with a concept, typically in the form of a drawing. And that's the way just about everything that is a product of invention and innovation begins. If not to bodies drawn with boundaries to what our formulas applied. In other words, to apply a formula, F equals ma or any other formula, you've got to have some picture of the body on which these forces are acting, the bridge or the rocket or whatever else it is. You have to have a concept of the idea of the thing before you can apply science or mathematics to it. Just think for those of you who have taken differential equations, you can't solve a differential equation without boundary conditions. You can't have boundary conditions unless you have a boundary. You can't have a boundary unless you have a concept of what the object looks like. This is just another example. This is the Hudson River at Poughkeepsie, New York. There are two bridges there. One in the foreground is a suspension bridge. The one in the background is known as a cantilever bridge. They operate on totally different principles. They all obey the same laws of motion, but that's not where they came from. They came from ideas that then enabled the engineers to check them with equations. What's the difference between science and engineering, then, to be explicit, between a scientist and an engineer? First, let's get this out of the way. Engineering is not science, nor is it simply applied science. If you go to some dictionaries, older dictionaries, you look up the word engineering, and you might find the definition applied science, period. As if, again, all you need is the science, and then all of these wonderful engineering developments will fall out of it. It simply doesn't happen that way. And here are some historical examples where engineering preceded science, basically. And if engineering precedes science, then it certainly didn't follow from science. The steam engine preceded thermodynamics. Steam engines were operating. There were steam engines back in ancient times, but the steam engines that we're familiar with today developed in the 18th century. And there was no science of thermodynamics. The science of thermodynamics was actually developed to help explain how the steam engine worked. Just because something can be designed and built and made and operated doesn't mean we have a full understanding of it, especially in its finer details. Powered flight preceded a full theory of aerodynamics. When the Wright brothers wanted to make an airplane, they actually wrote to the Smithsonian Institution, which at the time was the repository of scientific knowledge in this country, and they asked for, give us the science that is behind flight. They got back virtually nothing. They had to do their own experiments. They had to do their own trial and error. They had to effectively do their own science, if by science we mean knowing, understanding something. Rockets preceded rocket science. There were a lot of failed rockets before there were successful ones. Computers preceded computer science. Moon landing preceded a complete knowledge of the lunar surface. One of the objects of sending the astronauts to the moon was to collect lunar samples to know what the moon surface is made of. Well, then how do you design something to land on a surface that you don't know very much about? Those are the challenges that engineers are expected to rise to the occasion to achieve solutions to. Selective breeding preceded genetics, and so forth and so on. Science, more often than not, follows engineering, not the other way around. In some cases, scientists actually insisted that something could not be done by engineers. In the early part of the 19th century, one of the objectives was to develop a steamship that could travel from, let's say, England to America, not using sails, but using steam power. That would be a great advantage, because one of the problems with sails is you had to have the weather favorably disposed to get you from where you wanted to get to where you wanted to go. So if the wind wasn't blowing, well, you just sat and you couldn't schedule anything. But if you had a steam engine driving, paddles, then you could more dependably get from one place to the other. But scientists of the time, not all, but just some at least, said that steamships could not be built large enough to carry all the coal they needed to cross the ocean under steam power alone. The scientists argued that the larger the ship, the more power it required, the more coal it required, and you could never overcome this deficit. But by 1838, engineers had designed ships that operated on steam power alone, and that was the beginning then of scheduled transatlantic crossings. Scientists also said that wireless signals could not be transmitted over mountains or around curvature of the Earth. They believed that wireless signals went in straight lines. Well, that's true, they do. But just as if we're playing a game of pool, we know that we can carom something across, off the side of the table. You could bounce radio waves. In fact, it was that led to the discovery of the ionosphere, that you shoot up a radio wave and it gets bounced off the ionosphere and comes down on the other side of the mountain, let's say. Well, Marconi was instrumental in demonstrating that was a possibility. Theodor von Karman is generally described as on this stamp as an aerospace scientist. This was a sheet of commemorative stamps, and you know, on the edges of the sheets of stamps, there's the edge where there are things written to identify why he's being commemorated and so forth. And there he's identified as an aerospace engineer, and somewhere else he's identified as the architect of the space age and so forth. Well, very confused. What is he? Well, he was actually all of these things. He was a scientist, an engineer, and an inventor. He studied engineering, got his degrees in engineering, and he came up with a very widely quoted distinction between scientists and engineers. And since he was sort of both, it carries a lot of weight. Scientists seek to understand what is. Engineers seek to create what never was. Scientists want to understand things, but things as they are, generally speaking, things that are given to them, you know, the universe, the earth, and steam engines, if, you know, they've been invented. Engineers, well, they want to understand things too, but their more immediate concern is to make new things that generally improve the quality of life. Here's what I would say are some of the properties of a scientist, if I can speak that way. A scientist deals with existing things and phenomena. A scientist seeks understanding. A scientist frames hypotheses. A scientist tests hypotheses. Presents results, usually in the form of written reports or papers, publishes these things. In fact, that's the main product of science, is published papers. Eschews invention. the purest of scientists don't want to even think, or they'll tell you this at least, that there might be a practical application for their science, their discoveries, their understanding. That's not what interests them. What interests them is understanding alone. This is not an engineer's interpretation. There are plenty of quotations from things that scientists have written that say this quite explicitly. These people are today generally called basic scientists or pure scientists. But is creating a scientific hypothesis doing science or engineering? It's an interesting question, I think. Before it is stated, a hypothesis doesn't exist, at least in the form of a hypothesis. So creating a new hypothesis is akin to inventing a new thing. Testing a hypothesis, and this is what scientists are principally occupied with, is an application of the scientific method, which typically involves inventing an experiment. How do you test a hypothesis? Well, usually you have to do experiments, controlled experiments. You have to design those experiments. Be very careful. Again, you're creating a new thing. Publishing is like patenting. Inventors, engineers usually patent more than publish papers. So you can think of scientists, as having certain overlap with engineers and engineering. Scientists seek to understand what is, engineers seek to create what never was. Let's look at engineering then, on the other side. Seeks to create and design new things. We usually think of these as artifacts, tangible things like bridges and so forth. It's closely linked to invention. In fact, in certain ways, engineering is sort of like institutionalized invention. Has an element of art to it, but is not art for art's sake. Not always appreciated, but there is an element of art to engineering. Art in the sense that it's intuitive. It's not derived from equations. It's not totally rational. That's this idea of art. That's how engineers can conceive of things and create things. The conventional image of, the writer or the painter sitting before a blank sheet of paper or a blank canvas. Well, the engineer does the same thing. It has an element of science to it, but is not simply applied science. Engineering is actually a combination of art and science. Inventions and designs might be considered hypotheses to be tested by making and building the things. So, for example, when the scientists of the 19th century had this hypothesis that you couldn't build a ship that could run on steam power alone because it couldn't carry enough coal to run the steam engine, the engineers came up with their own hypotheses. And that was they built ships that were powered by steam alone and did make it across the Atlantic. Now, one thing about a hypothesis, and this is sort of a diversion, but you can never totally prove a hypothesis. You can only disprove a hypothesis. If scientists tell you you can't do this, how do you prove that? How does anybody prove that you can't do it? But you can disprove it by doing it. It's really as simple as that. Early 20th century engineering achievements were just legion. I mean, this is just a sampling of them. But if we look down here, powered flight, I've already talked about the Wright brothers having no scientific help, really. Water filtration was an engineering achievement in the early 20th century that reduced sickness due to waterborne diseases by a great amount. Engineers were working with health scientists, if you will. Water chlorination, the same way. Ford automobiles, nobody that I know of speaks of Henry Ford as a scientist. The Panama Canal, one of the big problems with the Panama Canal involved concepts. One of the first concepts was, where do you put the canal? It ended up being in Panama, but there were talks about a canal across Nicaragua and other places. And then you had to figure, okay, if we're going to build it across Panama, one of the things you have to go through is the Continental Divide, which goes through Central America. That means you got to excavate a lot of rock and dirt. One of the big challenges was, well, where do you put all that dirt and how do you take it from where you don't want it to where you can do something else with it? These are engineering problems. Broadcast radio, I mentioned that with Marconi. Modern rockets, I mentioned. The Empire State Building, definitely an engineering achievement. And again, a lot of that had to do with logistics and construction management. Hoover Dam, same way, and the bridges of San Francisco Bay. What propelled science into a dominant role then that is reflected in these newspaper articles and so forth? Or if you go, watch television in Nova, more often than not, you're talking about science, not about engineering. Well, it's these life images that I talked about earlier. That's one way. People were just, I won't say bombarded with these things because I don't know that it was a conscious effort, but this was just the mindset. This was the cultural environment in which engineers and scientists were identified or placed. And images like the Einstein-Steinmetz portrait. So let me say a few things about Einstein because I think it helps put some of these ideas in an interesting perspective. Einstein was the son of an engineer. He was familiar with the family manufacturing business. The manufacturing business was electrical devices. He went to school in a polytechnic, and he majored in mathematical physics. That's what his degree was in. It was actually a teacher's degree he got, but he couldn't get a job. In part because he wanted a university job, and he came from just a polytechnic. He didn't really have the kind of pedigree that was desired, and also he didn't have very good grades, to tell you the truth. So he became a patent examiner, not because that's what he wanted to do. That was the only job he could find after much, much searching. He got it through a friend. But it was through examining patents, being a patent examiner, that he actually became the scientist that we know him to be. And I'll give some quotations that substantiate that. He also became an inventor, literally an inventor, of both theories and things, as I alluded to earlier. And he became a patent holder. Einstein took out patents. And he took them out very seriously, as I will illustrate, especially with Leo Szilard. According to Einstein's uncle, who was in the family business making these electrical devices, where I and my assistant engineer had racked our brains for days, this young fellow, young Einstein, comes along and solves the whole business in a mere quarter hour. So his uncle predicted he'll go far one day because he saw the promise in this guy. He didn't see him as being a scientist, he really saw him as being an engineer, but that's neither here nor there. At the patent office, Einstein had to examine these patent applications that were really claiming to be something new, worthy of being granted a protective patent. And the challenge to Einstein, in part that he set for himself, was, well, how is this consistent with science? This thing is going to do all of this stuff. Well, Einstein also enjoyed life. He had a sense of humor and wanted to have fun. According to one historian who studied Einstein, he said, Einstein was challenged and amused, not primarily by practical utility, but by what he called the fun of inventing. Einstein found it fun to invent. And by invent here, we're talking not only about physical engineering things, but also about scientific things. His scientific theories were inventions to him. Some of Einstein's patents were very practical. Refrigeration system, electromagnetic pump, electromagnetic sound reproduction, light intensity, self-adjusting camera, and these were written up in newspaper. This was not before he became famous, not before he became a Nobel laureate, but after he became. That's why they were newsworthy, because here's this scientist and invents an automatic electric eye camera. That was news, because it was like a man bites dog story. It was not what was expected. So this is Szilard. This is a famous photograph. Einstein and Szilard, they were actually conferring over the draft of a letter to President Roosevelt, warning that what they know from the scientific grapevine, if you will, and it's even more public knowledge than that, was that the Germans were developing a bomb based on nuclear fission. It would have radioactive implications. And they were writing to President Roosevelt telling him that you've got to start research in this country on the nuclear fission and radioactive materials. You've got to start assembling radioactive materials, and you've got to develop a weapon based on these scientific principles. The reason they knew each other so well that they could collaborate like this was that they were partners in invention. All patents, and this is the formal agreement that Einstein and Szilard came up with. All patents relating to refrigeration would be considered joint property. The idea here was that they would talk about these things so much together that after a while it became difficult for them to say, oh, well, this was my idea or this was your idea. These concepts became part of both of them. And as a result, they just said, well, we'll just consider a team, consider ourselves a team. Szilard would receive the profits first from these patents, if there were any, and only up to an amount equal to a university assistant's salary. Szilard was sort of out of a job at the time. He had just gotten his PhD. Einstein was on the faculty, so Einstein had a steady salary. And in order to share in this way, this is the agreement they made. But then when Szilard made equal to the university assistant salary, then he and Einstein would share equally. This, to me, illustrates how seriously they took this inventing. They were not just having fun inventing, they wanted to make money off inventing, and they didn't want to have arguments about how to split the profits later. This was all spelled out prior. Refrigerators in the 1920s were actually dangerous things. They were poisonous because of the refrigerant. And they were also, there were a lot of mechanical parts to refrigerators, and the pumps would reciprocate a lot. And what this did is it led to leaks. And if you leak this poisonous refrigerant, well, of course, then you can poison the occupants of a house if they happen to be sleeping at the time, which is what happened. And there were numerous newspaper reports to this effect. Well, this caught the eye of Einstein and Szilard, and that's why they began to work on refrigerators. This is fairly typical of where an engineering problem comes from. It comes from a literal problem that you want to improve upon, you want to find a solution to. How can you make refrigerators that are not poisonous, that won't develop leaks, that won't be noisy, and so forth? The refrigerators of the 20s, when Einstein and Szilard were talking about this kind of thing, were basically ice boxes, and an ice box is nothing but like a cooler. You put ice in and it keeps things cool. But if you put a motor on top of it, an electric motor, it can do away with the ice as a cooling element. Back then, because this was the latest technology, if you had a refrigerator in your kitchen, you wanted everybody that came into your kitchen to know, and they knew it by seeing the guts of the machine right on top. Well, there had to be a better way, and what Einstein and Szilard came up with was not to change the physical appearance so dramatically, well, that would follow. They wanted to eliminate the mechanical pump. That would eliminate vibration and noise, shock, and all that other stuff that leads to leaks. and they employed the principles of thermodynamics to help them do it. They actually received a patent. This happens to be the US patent they received, but they also received patents in Europe, and in particular in Germany. And their patent was actually acquired by the German equivalent of General Electric. It might have been actually produced and marketed, except, and this is where things are subject to accident and chance and timing, this poisonous refrigerant of the 20s was replaced by a new one, Freon, which was not toxic to humans. It was not only later that it was found to be toxic to, the environment. But the idea, if you just replaced the toxic refrigerant with Freon, you wouldn't have to change the mechanism. Everything could stay the same. You just refill it with something different. Whereas to manufacture and produce and market the Einstein Szilard refrigerator, you'd have to retool your factories. So, as often happens with patents, the General Electric German company controlled the patent but never made the refrigerator. If they had, we'd probably know differently about Einstein. So, are inventions created or discovered? Are theories discovered or created or invented? Well, Einstein had an opinion about this, and he wrote about it, and this is more documentation that these are not just speculations. Einstein was talking about Ernst Mach, who you could describe him as a philosopher of science. Mach's weakness, as Einstein saw it, lay in the fact that he believed more or less strongly that science consists merely of putting experimental results in order. Do a lot of experiments, you plot them all, and you look for order in them, and out flies a theory. That is, he did not recognize the free constructive element in the creation of a concept. He thought that somehow theories arise by means of discovery and not by means of invention. And here, I think Einstein is supporting the idea that science has a lot of kinship with engineering, creating something new. Thomas Hughes, another historian of science and technology, judging from Einstein's use of physical metaphors in his scientific writing, his preference for visual thinking, and his familiarity with inventions, safe to assume that he fully recognized the similarity between the intellectual activity of the creative scientist and that of the creative inventor, or read engineer. There's another prejudice against engineering is that, scientists are engaged in a more intellectual activity than engineering. Well, Einstein didn't think so, and Einstein, did both. For Einstein, a hard and fast line between technology and science simply did not exist. Okay, back to von Karman. Scientists seek to understand what is. Engineers seek to create what never was. So you have refrigerators, which are basically an engineering invention, creation, concept. With the science of refrigerators, or thermodynamics, that can lead to improved refrigerators. But what's starting here is the engineering, not the science. Einstein and Steinmetz again, just to remind us. Let me say something about Steinmetz. He was basically a mathematician by training. He also was General Electric's chief consulting engineer. Whatever thorny problems General Electric had, they would call for Steinmetz to get his input. Not unlike Einstein and the family business. He could solve these problems very quickly. He could see to the heart of the matter. There's an old story about Steinmetz that's often repeated, that he used to serve as a consultant, and somebody would call him in on a job. He'd look at the situation, ask questions about it, and turn a knob. Everything would work fine. He'd send them a bill for $10,000 for a consulting fee. And people asked, well, what did you do? You only spent 5 minutes turning a knob and you won $10,000? He said, well, I'll give you an itemized invoice, and that basically read time spent thinking about the problem was like $9,500, $500 knowing which knob to turn. That was the balance of the thing. In other words, it was experience. The experience is what you pay for. Steinmetz became very popular as a radio commentator. He would talk about things, and he was not only interested in engineering, he actually ran for a state office in New York, where General Electric's offices were in Schenectady. His name, Steinmetz, became synonymous with engineer. When I was actually going to school, some of the people that were not studying engineering would call engineering students Steinmetzes, because that had become so much integrated into the language of certain people in the first part of the 20th century. And these were the children of those people, and they had heard it around the house so much that it became part of their vocabulary. He was an eccentric. He used to go out in his canoe and work. He didn't abide by many of the rules. He was of General Electric. They said you couldn't smoke around the facilities, and he said no smoking, no Steinmetz. And he was so valuable to them that he could get away with it, of course. He was, on this series of commemorative stamps, this group, he was one of the inventors that was named. I think what's interesting here is the three other inventors. If you look at the upper right, they're pictured with machinery, things, if you will. Steinmetz is pictured with, well, what looks like a graph of a sine curve, something similar to that. One of Steinmetz's big contributions was his strength in mathematics led him to understand how he could develop techniques to very efficiently transmit alternating current. And he did it with mathematics. What's the difference between an engineer and inventor? I've sort of sloughed over that a little bit in here. An inventor can write in a patent, quote, whatever the reason it behaves as it does, it is extraordinarily well adapted to the purpose. This is an actual quote from an actual invention, a patent, where the inventor is saying, well, I don't exactly know how this thing works, but it works. Therefore, I deserve a patent. One of the things that distinguishes an engineer is that the engineer wants to know the theory behind it. And this is one of the reasons why engineers are subjected to so many science courses at the beginning of their curriculum. It's not that engineers don't want to know science, but they only want to know it so that they can create new things. If it'll help them, they want it. Remember, engineering is art and science. Steinmetz was interested in both the science and engineering of lightning, for example. So are scientists and engineers actually just mirror image twins of each other? Well, you can make that argument. Steinmetz became famous. One of the reasons he became so popular, that his name became synonymous with engineer, was that he was photographed with all sorts of very well-known people, from inventors like Edison and Marconi, to movie stars like Douglas Fairbanks. And wouldn't it be nice if there was a portrait of Steinmetz and Einstein, is the way the General Electric publicity department thought. the implication was, by the way, that most of these people were making a pilgrimage to visit Steinmetz. So this General Electric publicity photo was in that tradition at General Electric. What gave science more prestige, status, and influence than engineering? Why was Einstein, the more prominent figure in that portrait? Well, a lot of it stems from World War II, in my opinion, and I think in the opinion of a lot of others too. The atomic bomb, radar, these were very, very important developments. I would call them engineering developments because they were the development of things that were new. They were not just understanding, they were leading to new products. They're commonly associated with scientists. The atomic bomb with the Manhattan Project, and there were many scientists associated with that, especially in managerial positions, but in fact it was an engineering project. The objective was an engineering objective. Radar, pretty much the same way. After the war, science had a very good reputation. I'm skipping a lot of details, but I have to adhere to some time constraints here. Giving a talk is another engineering problem. You got all these constraints. Gilbert toys were erector sets, chemistry sets, and so forth. This is a booklet that Gilbert produced. Science leads the way. Now, what's the implication of this? And again, we look at images. Here are these boys, they're looking through microscopes and, conducting chemistry experiments. And what's this stuff on the left? Well, I think the implication is that what these boys are doing is going to lead the way to rockets and airplanes and so forth and so on. Words matter. One of the Gilbert products, the chemistry set, said, "Today's adventures in science will create tomorrow's America." Well, I'm not sure it's as simple as that. But does science or engineering realize the future? Does science or engineering lead to innovation? Now, innovation is a word that we've been hearing over the past several years, with the economy sort of depressed in the U.S. One argument you keep hearing is, well, what we need is more innovation so we can get the economy back on track and we can prosper again the way we once did. After World War II, there became a linear model of research and development, or the road to innovation is another way of putting it, because generally speaking, research and development is for an objective. And one of the things that Steinmetz did for General Electric, for example, was spell out to them what a research and development lab should look like, how it should be organized. All the industries pretty much in the late part of the 19th and early part of the 20th century were developing R&D labs, not for the sake of science, but for the sake of coming up with new products, new ideas, innovations. This linear model was that research leads to development. It was really what it was saying was that science leads to engineering. And after World War II, one of the big players was an engineer named Vannevar Bush, and he was charged with President Roosevelt of writing a report advising what would be the thing to do now after the war is winding down so that we can continue the prosperity of America after the war. And Bush came up with this report whose title was Science, the New Frontier. And in it, he implied this linear model. You got to support science because that is eventually going to lead to development of inventions and innovations. He admitted that you couldn't tell, how that was going to happen exactly, but you had to have faith. Well, I'm going to have to start skipping some because I see I'm running out of time, but if you were back in the 1950s, what innovations were in America's future would be hard to predict. Jet airliners were just beginning. The turbojet engine was developed in the Second World War, but it never really got very far. It wasn't until well into the 1950s that it became applied to passenger flight. Interstate highways and so forth, all of these things. These would be engineering achievements. In many cases, there wasn't that much science behind them. The National Academy of Engineering looked into what were the greatest engineering achievements of the 20th century as a way of celebrating the millennium. And again, you look at this list, and not too much science is evident. It was engineering more than science that realized the future. Innovation takes more than science. It takes engineering and entrepreneurship. There's a difference between invention and innovation. Generally speaking, the word invention connotes something that's new and not obvious. These are actually criteria to get a patent. But it doesn't mean that it's going to do anything more than be a patent on file in the patent office. Something that is invented and usually patented that then goes on to change the way we do things, the way we interact with technology, that's called innovation. So the iPad was an innovation. What do informed people think of scientists and engineers? Now, what I mean by informed people is, what if you tell them stories and then ask their opinion? Knowing the accomplishments of people means a lot. The British Broadcasting Corporation ran a TV series in which they profiled famous Britons. They called it Great Britons. And the idea was they would give these biographical documentaries, and then they had a conducted a survey at the end of this series and asked people to vote for the greatest Britons. So, you rank your choices. Well, Winston Churchill came out #1. But #2 was Isambard Kingdom Brunel. Who's Isambard Kingdom Brunel? Well, he's an engineer, or he was an engineer. He was one of the great heroic Victorian engineers. He's very interesting engineer. He had a lot of successes, such as one of the first steamboats that crossed the ocean. He also built railways and bridges, designed and built them. He designed the largest steamship till then, and it was launched in 1857. He was not without failures, embarrassments. Not all of his ideas worked as well, but he's remembered as one of the great Britons of all time, in large part because he really reached beyond just the ordinary to try to create great things. So he beat out Lady Di, he beat out Charles Darwin and Isaac Newton, scientists, William Shakespeare, Queen Elizabeth, and John Lennon, for crying out loud. So if you tell people about engineering, and then you ask them in their opinion of where it ranks relative to some of these other things, well, you get a different opinion. The National Academy of Engineering elects of the order of 65 new members each year. In the class of 2012, I just counted up quickly, and about 20 of the 67 inductees had no engineering degree. So this comes back to what we talked about in the beginning with the Russ Prize. The recognition of the prize is for an engineering accomplishment, not for an engineer. You're not recognizing an engineer, you're recognizing an engineering accomplishment. And the same with the National Academy of Engineering. They're not recognizing engineers, they're recognizing the engineering accomplishments. And engineering accomplishments can be made by scientists or engineers, or neither. But anyway, 20 of these had no engineering degree. Virtually all held patents, meaning, they were trying to create new things. Joint membership with the National Academy of Sciences and the Institute of Medicine is interesting. There are a lot of people, relatively speaking, who belong to both the National Academy of Engineering and the National Academy of Sciences. So these same people can be recognized for engineering accomplishments and science accomplishment. And after hearing about Einstein, this should not be that surprising. The same with the Russ Prize, as I mentioned. So the classification of things can be misleading unless we think a little deeper about it. Things and people and their images are not always as they seem. And let me conclude before opening up for questions a little bit about this image, which I've shown so much. Einstein represented science and research, Steinmetz engineering and development. General Electric wanted to emphasize that what they were doing was as exciting and as interesting as what Einstein was doing. They never actually stood together, posed one-on-one. They were actually part of a group. This was actually part of a group photo. The Radio Corporation of America was demonstrating a new transatlantic radio transmission system. And Einstein and Steinmetz were actually standing, well, not far from each other. They weren't actually, whether you say they're standing next to each other or not is a matter of, semantics. Well, General Electric creatively cropped this. This is before the days of PowerPoint, by the way. These are not digital photos. This is a, wet process. Oops, I skipped that. So then you get this photo where they're closer to each other, and then you sort of get rid of the peripheral people, and then there's that funny guy in the middle named Tesla. Well, you get rid of him too, and what you end up with is this image of Einstein and Steinmetz. I've already mentioned that I asked GE to reproduce. I wanted to reproduce this. I didn't know the history of this photo at the time. And whether GE did or not in the 1980s, I don't know, but they didn't tell me if they knew it. But this image of who's a scientist, who's an inventor, who's a scientist, who's an engineer, it gets very muddled when you look beneath the surface, when you look past the cliched images, let's say. Who is the scientist? Who's the engineer? Does a scientist really do things that are that different from an engineer? Vice versa? Are science and engineering more alike than different? Well, I'm not going to try to answer that question because I think, we could go on and discuss that. But I think it's a fair question to ask, that they're not necessarily so different as we often think they are. One is not necessarily so much more superior to the other as is often the presentation. Well, let me end there because I was told I should ask for questions, welcome questions. So thank you very much for your attention, and I hope it's been interesting to you.
So you addressed the what appears to be a bias against engineering in the media, science writers, that kind of thing. I was wondering if, have you speculated on that? Does that have to do with the fact that in primary and secondary education, students take science courses, but they never take engineering courses? Any thoughts on that matter?
Yeah, I think that could be, certainly part of it. I think another part of it, which I probably didn't mention, is that scientists seem to have bigger egos than engineers. So given the opportunity, they will take the advantage. That's something that obviously can be overcome, as we can indoctrinate, we as engineering educators can indoctrinate engineering students.
Well, I have one more question, which hopefully is less controversial, and that is, you were talking about the atomic bomb and the radar being engineering achievements during World War II. In the engineering education history that I've researched, the assertion is that engineering education prior to World War II was more akin to technician training, and that when World War II came along, the engineers didn't have the proper science background to be able to do the innovation that was needed during the war, and thus the scientists had to be brought in. That's the assertion that some engineering education history will say, and that post-World War II, engineering education had to focus a lot more on basic science, as we do to this day, to provide the necessary background. And I'm wondering if you agree with that assertion or any comments you might have on that.
Well, with regard to pre-World War II engineering education, I recently had reason to look at some curricula from the 19-teens into the 1920s, and I actually wrote an article that, at least for this particular curriculum, which was for Stevens Institute of Technology, the mechanical engineering curriculum was not that different from what it is today. So I would not agree with that, at least anecdotally. I think with regard to engineering education being more scientific after the war, that's certainly true. But that was influenced in large part by this Vannevar Bush's report, by the belief, false as it may be, that science led to development and to innovation. And also, that's where the money was in large part. The National Science Foundation was set up. It came out of Vannevar Bush's concept, in a way. It was debated politically over a period of 5 or so years. But finally, the National Science Foundation was developed. And to this day, engineers think it should be called the National Science and Engineering Foundation, and that it should recognize that science and engineering are different, and that they should be funded in different ways. Not the same expectations, in other words, should be expected of each of them. So on that ground, I agree with that. The underlying reasons we may differ a little bit about. What was your other question? It was about whether the engineers weren't prepared scientifically. Well, the atomic bomb depended so much on nuclear physics. There's no question about that. And nuclear physics was definitely not a course that engineers studied, whatever their curriculum. So there's a certain amount of truth to that. But the project, and then the mere word that it was called a project, suggests there was an end product in mind. In that sense, it was an engineering project to me. And I'm in the context of the vocabulary that I've introduced here. Well, I think, okay. There's a question over there next. He had his hand up.
Thank you for your very interesting remarks. I'm an emeritus engineering professor here at this university, and I'm wondering if your work in history and so forth at Duke University might have brought you to think about how our culture, what our culture asks of us as engineers. A very broad question. For example, I say that because I look at the current federal discretionary budget in the United States that Obama sent down for the year 2013, and 60% of that budget goes to military research, military work of our discretionary budget. And then I took a look at the 2009, some time ago, the 2009 budget for the United States government, the regular budget, and I found it's about $700 billion in 2009. And I look at the research and development budget for the Department of Defense, it's $81 billion. Then I go to the National Science Foundation and look at the NSF budget, non-military generally, it's $7 billion. The Department of Defense has 13 times more research and development budget than does the National Science Foundation. Therefore, and I'm very interested in current things like consuming planet Earth and global warming and these issues, and I'd like to know if you think about what our culture and how do we get our culture to ask us to do what we need to do to live into the future.
Right.
Thank you very much.
Well, your initial question was something to the effect that what do we do to get our government to ask, what is it asking engineers? I would say our government is not asking engineers the right questions and not giving them their head the way it's giving scientists their head. That's my quick response to what you're saying. There was a very interesting, after this Vannevar Bush's report, science funding for basic science, it just, went through the roof, relatively speaking. And then after a while, it was actually, I think, the Air Force that asked the question, is this really working? Is really science leading to the innovation we're looking for? And they conducted a survey called, I forget the name of it now, but it basically found the answer to be no. All of the basic scientific research had led to a minuscule number of new products for the Air Force in particular. That was largely challenged and ignored, in large part because the scientists didn't want to hear that. As I sort of alluded to with the earlier question, scientists have bigger egos. They also are more cunning than engineers generally, and they often are in more positions of control. You look at the White House has a science and technology advisor. Almost always that's a scientist, for example. So these questions that you're asking about priorities and so forth, I think are very good questions, but I think engineers and engineering are going to be at a disadvantage until they develop the kind of ego, let's say, that scientists have, and develop the kind of people and political skills that a lot of scientists have.
I call it engineering and public policy.
Well, people use that term, yeah. There was a question over there, that fellow in the white back there.
Thank you for your presentation. Maybe I'm being picky, but you made the statement that computers preceded computer science. But didn't John Bardeen develop in Illinois in physics some science that helped produce computers?
Well, as I indicated, engineering is always a combination of science and art and science. And yeah, I'm oversimplifying in some cases, but my point was in that is you can't have a science of studying computers if you don't have computers. That's all I meant. I mean, and computers go back to Babbage too, before Bardeen.
Alfred Nobel would seem like he made his fortune with an engineering type achievement. But he funded science prizes. How did he make it?
I couldn't have planted a better question. Alfred Nobel was basically earned his money in engineering. He was fundamentally a chemical engineer. He wrote a will specifying that there should be prizes, and the Nobel Prizes that we're familiar with today, he named by name. But what he specified was that they should go to the greatest achievements of the previous year. They were like Oscars. They were like Emmys. It was what happened the previous year. And by that, it's pretty clear to me, he was thinking about tangible products, not about theories that had yet to be proven even one way or the other. And what happened was Nobel's will named 2 executors, both of them engineers. The engineers, these engineers, for whatever reason, did not feel up to the task of taking on such a responsibility. They didn't have the egos to connect it with some of my other comments. So they got lawyers involved. Now, the lawyers, everybody travels in social circles. The social circles that the lawyers traveled in included scientists, but not engineers. So when the lawyers tried to get some familiarity with the issues involved, they took the advice of scientists. Now, what are scientists going to do? Well, they're going to favor science as opposed to engineering. When the Nobel Foundation was created, so it was these lawyers and these scientists that had the maximum input into that. Early Nobel Prizes, remember the first Nobel Prize was given away in 1900, I believe. Some of the early newspaper reports actually questioned, why are these prizes being given to scientific achievement as opposed to more practical engineering achievement? These questions were actually asked in the early 20th century. So I hope, in the context of some of the earlier things I said, it was basically that it was, what's the word, hijacked or something like that. In my opinion, Nobel's will was not really, is not being followed the way he intended it. That happens a lot. So if you make multi-millions and you want to endow prizes, make sure you write your will very thoughtfully and make sure you pick your executors very thoughtfully. It's the only way to assure that what you intend is going to be actually the way things are. I might add, while the microphone's going, that because of the Nobel Prizes going to science, that was another thing that, of course, helped elevate science over engineering.
Okay,
Just the opposite effect of what Nobel had.
I have one question. I too enjoyed your talk, but I have a question about Einstein. So you're painting him as somebody who didn't maybe differentiate science and engineering.
Oh, I think
two
he
separate entities, or
no, he
didn't have
understood.
any prejudice against engineering, right?
I don't think he had a prejudice against either engineering or science. He saw them. I think he appreciated the differences. I think he understood, though, that there was a lot of similarities, overlap.
If I recall correctly, when his son Hans told his dad that he wanted to study engineering, Einstein got really upset, and they didn't talk for at least 5 years.
Well, yeah, Einstein also became a snob, didn't he? I mean, basically.
Thank you for coming. I've been advising undecided students this week, and some of them will come in the office and say, oh, I'm kind of interested in engineering, I'm interested in science. How would you describe the distance between the two, and which one would I like more? I'm sure you've heard those questions too. How do you address those?
Well, I would probably refer to von Karman's distinction about, science studying what is and engineers creating what isn't. And I don't know, I find a lot of young engineering students that are unsure. They do want to make things. They do want to create new things. But then the early engineering curriculum, of course, is a lot of science, and they don't see it fulfilling what they thought it was going to be. Now, a lot of engineering programs are trying to overcome this by introducing a lot of design as early as the freshman year now to show the students that engineering, to try to promise them that this is coming. But without that, it's just a promise.
Thanks everyone for coming, and I'd like to remind you that there are refreshments out after you exit from the theater, so thank you very much for being here, and thanks especially in another hand for Dr. Henry Petroski.
Thank you very much. Thank you.